I'm Thomas Gorin, and today I will talk about Hopfield networks. A big part of a master thesis project by Jose Luis, and it's in collaboration with Ms. Marina Reitz. Well, one reason to give this talk is maybe a Nobel Prize, which was earned by John Hopfield, and who was the other guy? The other guy who won the Nobel Prize? Hinton, yeah. So they are both researchers in artificial intelligence, and even though the original works or the original interest of at least of John Hopfield were also motivated by physics, phase transitions in such systems. I will not really talk about the work of John Hopfield. I just want to show you the Hopfield network as such, and particularly our project. When exactly I will just go off. Here's the Google Scholar page of John Hopfield, so you can look what he has been doing, and I think the important paper is the first one. That's also the majority of citations. And yeah, so if you're interested in his work, just have a look at this assignment. Okay. Okay, so the problem we are dealing with is, say, associative memories, and we just want to understand how they work and maybe see the differences between those kind of memories and the usual memories we use in digital, well, in computers. And why is it interesting to us? Well, you will see that we can apply some techniques we have been used in several contexts. That is, say, study and classify correlations to understand complex systems. So you have a complex system, and one way to analyze the system and how it behaves is to, well, of course, you take some signals from the system, and you can look at the correlations between these signals. And maybe you don't really know if this system, you can define something like states, right? So then there is this K-means method coming in, which looks at how similar are correlation matrices, say, taken at different times. And so if they are similar, you say, okay, the system is in the same state. And if they are very different, then you say the system is in a different state. And since this is an algorithm, this K-means process, it gives you automatically, say, a sequence of states the system would be in. And you can look at it in some sense similar to dynamical systems, right? So if you have a dynamical, chaotic system or complicated system, one way to learn something about that system is to do some symbolic dynamics. But if you reduce enormously the number of states the system could be defined in, so you are coarse graining the state space enormously, And then it makes the analysis simpler, right? This is somehow the same idea. Now you have a stochastic process, very complex system. And this k-means method, it allows you to reduce the state space. So you're looking at less states and how they evolve in time. And that makes it, in some cases, easier to understand something about the system. So this is, say, a rough idea. And we want just to try how it works in this context of a Hopfield network, which is, I mean, will work, or we look at it as associative memory. Okay, so I will, in the next slides, I will show you the mathematical formulation, how you store and how you recover information in this network, and how you can estimate its capacity. And then this is the main part of the work, how you can analyze this network and find out, well, properties of it, right? So in particular, we will be interested in studying the amount of information stored in the system. So think about a hard disk, for instance. If it has if it is encrypted, you don't really know if it contains information or not. And in a similar way, if you have this Hopfield network, just as a black box in front of you, you will see that it is hard to learn whether, or to analyze whether information is actually stored in this network or not. And the aim here is to quantify, right, the amount of information stored, provided that you can somehow extract this information. Okay, so well, I think now I explained too much in the previous slide, so this is what I wanted to explain. So it's Hopfield network and associative memory. We will store k random patterns on that network. The fact that they are random, it makes it difficult to know whether it's really a pattern or whether it's just noise. We assume that we have no prior knowledge about these patterns, so that's crucial. Of course, I mean, the usual way you use associative memories is that you know something in advance, you tell that to the memory, and then the memory gives you back the pattern which more closely relates to what you know. So we will see that the direct retrieval breaks down. You cannot just scan the memory and to extract all patterns. And so we want to try a combination of tools, and these are these k-means clustering algorithm, the correlation matrices, and so that's, I think, also I mentioned. I mean, for instance, this combination of correlation matrices and the k-means clustering has been used to assign, say, symbolic states to the evolution of an index of what's it called, of shares, right? The Dow Jones index, and the companies stock listed there. The development of their prices has been analyzed in that way, and then people could define different states and how the system changes from one state to the other in time. Okay, yeah, literature, that's that very famous paper that you just saw, and this is a paper which came out somewhat later, which applied mean field theory to this, to understanding the dynamics of this system. And one important result we will use in several times, or mention it several times, is that was already found by Hopfield, that if you have a network of 100 neurons, 100 nodes, then you can store about 13 patterns in this network and retrieve them. A more precise estimate is this number, where you see that it's less than proportional to n, but it's almost proportional to n, this capacity. So now let me give you a mathematical formulation of the Hopfield network. Okay, so the idea is to store these k patterns of length n, and these are now k vectors of length n, and we use binary elements. So each entry is either 1 or -1. And then you can define the matrix. Okay. And, this is the Hopfield matrix. And now it represents, so it's this will represent your network, which has the patterns stored in it. Right? Of course, now the question is how you can retrieve patterns, and how you can store more patterns, how you can remove patterns, the usual questions for an information storage device. Right? So to add a new pattern, we just, here we have a new pattern xk plus 1. You just add that vector to the, well, not that vector, you add that matrix to W. Right? To remove a pattern, well, you just do the same, but with a minus sign, so you remove the pattern. Now, to retrieve the pattern, that's a difficult issue. Right? You can see that, for instance, this pattern, it is not stored in one single place of the network, but it's stored all over the network. Right? You can see that each element of this matrix W will be changed according to that pattern. So each element of the network contains some information about the pattern, the new pattern you stored. And but what you can find is that if you build this function, so it's just a quadratic form of the W matrix, it will have local minima at all the positions of the pattern. Right? So this is a function of a vector y, and if this y coincides with one of the patterns, then there you will have a local minimum. That's not always the case. This is the typical case. This is what you want. And to what extent this is really true, it depends on, for instance, how many patterns you store in your network. Right? If you put too many patterns, then this will fail. And then still you have the problem, okay, you know now, given this W matrix, the patterns are the local minima of that function, but you still have to search for them, right? It's not, so mathematically maybe the job is done because you know how to get the pattern back, but in practice, you really want to know what would be a good process to retrieve these patterns. Okay, and that is our Markov chain Monte Carlo method, right? So well, ideally, you should start with a vector which is close to some of the patterns. That's the general idea of an associative memory, that you will not start randomly as if you have no information at all. You will start with something which is similar to the exact the pattern you want to look at, right? And then you try to do elemental steps, which are local spin flips, so local changes of your pattern, which is evolving, and you want to get it close to the local minimum. So you do these changes, right? So this just means that the component J will change its sign. Okay? And then you do this local change. Now you calculate that quadratic function, your energy function, and if the change leads to a decrease of the energy, then you accept the change, and otherwise you reject it. Well, now we are in the position, or we want to put ourselves in the position that we don't know anything about the pattern stored. So that's why we choose a completely random initial state, why not? And then we do these local changes, right? And we just repeat those steps until we are at the local minimum of the system. That means we can check, right, if there is any possibility to change one single spin and the energy will decrease further or not. So if we are at the local minimum, then the process stops. Okay, now there are cases when the energy change is just zero, and then the one way of the method is to decide at random whether you accept that change or not. In this artificial intelligence community, it's more common to always do the change in such a case. But this will essentially produce the same result. Okay, maybe another point to make here is that you can calculate the change in the energy very simply, right? You don't really need to calculate the full function for one state and then for the other state and then take the difference. This will be not efficient. You can calculate it directly, right? Just do this computation. Okay. Okay, so at the end, there are several possibilities for the trivial process to end. One is that you're reaching a local minimum, and then there are still two options, because this local minimum can be one of the states you stored, or it cannot be, right? If you store too many patterns, then it's quite possible that there are local minima which do not correspond to the states you wanted to store. And then there is another possibility that you reach an extended local minimum. So that's say what's called a collection of configurations where the energy remains constant. Okay, this I don't want to explain. Okay, so we want to, as I said, estimate the capacity. No, sorry. So, okay, I will explain now how you can estimate the capacity of this network. And the idea is simply that this pattern retrieval is a search process for local minimum. And that's the important point. We are allowed to start arbitrarily close to them, to those minimum. And then, if you assume that all stored patterns are random, you may calculate the probability that all k patterns are local minima for a given network size n. Right? So, say you have k patterns of size n. You construct your Hopfield matrix, and then you calculate the probability that all of these k patterns are local minima. If this probability is sufficiently large, then you can say that, okay, I can store this amount of patterns in my network. If the probability is too small, then you say that this is too much, right? So you expect, okay, so, yeah, so that's it. So you expect like, sorry, just a second. You expect such a behavior, okay? So now here what I plot is the number of patterns divided by n, is it? Because as you saw, we expect the number of patterns to be stored, to be able to be stored, being proportional to the size of the network, and the probability that all the k patterns are local minima, right? And so you can see that for small values of k over n, this is 1, and then it drops. And it becomes very quickly equal to 0. Right? But you see that this theoretical value, 0.138 n, but it's like the limit where this probability is still finite in the limit of large network size. For instance, look at the yellow curve. It's 1,200 nodes or 1,200 neurons, and the probability that all patterns are local minima, right? Yeah, it's very small, but still fine. And anyway, this always also means that the majority of the local minimum are really the pattern you wanted to store. I mean, this is a slide where I wanted to explain how you can calculate this probability analytically. But I mean, you essentially use that that all these elements, I mean, all elements of all patterns are random values, +1 and -1. And if you have a sum over them, then you're summing independent random values, right? And then you have the central limit theorem, so this becomes a Gaussian distributed eventually. And now you can work out the numerics and obtain the result. But it's not easy, but and it's a bit tedious, but it can be done. So let's just not do it today. And okay, so as long as this is finite, right, you can, in principle, you can recover the pattern. Eventually, you just have to try sufficiently many times. And yeah, another point is that you really have to start close to the pattern in order to for this to work. Now, but this is our situation, and this is completely different. Right? So now this is the probability to end up at one of the stored patterns with this recovery process, starting from a random initial state. So if you have no knowledge. And then again, you have these different network sizes. Now here it is just K, it's not K over N. Right? And you see that this probability, it goes down very quickly. I mean, even the yellow and the green curve, they go, well, I should have plotted a bit more, but they go to zero very quickly. I mean, if you want, if you have 1,200 neurons, you want to store, yeah, like 10, 15%, so it's 150 patterns maybe, and the curves are really stringent. But for the next, for our example, we just look at the blue curve, which is n equal 80, and right for A22 patterns, there is zero possibility to recover one of them. Yes. So this is it. Now, what's the idea? Now we do a lot of recovery processes. Okay? And now if the final states have something to do with the patterns stored, then they should somehow be similar, right? Because say you take here 100 initial states, maybe 1,000, and you have of the order of 22 patterns stored, then many of them must be close to the same pattern. If they approach the pattern at least. And that might be something you can check. And that's why we think about correlations, right? Because if many of these final vectors are similar, then the correlations between them is large, and that is something you can keep. And that also means that this will be the second part of the results. The first part just states that these vectors are similar, and so you can directly apply this k-means algorithm, and it will put them into the same cluster. Right? So again, you have this 1,000 vectors. You apply a k-means clustering, so you're looking for vectors which are similar, and put them into groups of similar vectors. Now, if this is successful, right? So this will be successful if the vectors are really similar. But if they are not similar, then this will be unsuccessful. And that is something we try to measure. Okay, now this is the k-means clustering algorithm and what it tries to do. Okay, so you have where these n vectors, you have a measure of distance of how different these vectors are. And you want to partition the full set of vectors into k groups. Yeah? That means that you beforehand you need to know the k. And that is something we will just play with. So for us, k is an independent variable, and we look at the results for different k.
Perdón, ¿se dejó de compartir en clase?
Oh. Se dejó de compartir. Okay, and now, what will be the best partition? So the best partition will be that one where the distances between the vectors in one group is smallest. Okay, yeah. So what you really do is for each group, you calculate an average vector. So that will be, so if you have many vectors and you calculate this average, so this vector will be like the center of mass of these points, right? And then you calculate the distance between each of the vectors of the group and its centroid for all groups. Right? So L is goes over the groups, J goes over all elements of the group, and this distance between the element of the group and its centroid. This function we want to minimize. And there are several algorithms how to do that, at least approximately. And they go all under this name of K. Okay, and so what we plot here is this cost function, this distance within cluster sum of squares. And well, it has the general property that if you have more clusters, then this distance will be smaller. And in practice, what you often do is you make such a plot. If you don't want how many clusters you would be appropriate, and you expect that first there is a steep drop and then it's slowing down the drop. That's like the elbow plot called, right? Where the steep drop goes over into a slower drop. This would be a good estimate for the number of clusters to use. And here you see that there is no sharp transition really, but what you can do is because here we have different number of patterns stored, and for each of these cases we look at how many clusters we would need for the classification. But you can put this plot on, you can rescale this plot in such a way that all the curves are on one line. And it's a simple rescaling, so just here we divide the number of clusters for the k-means by the number of clusters stored. And here we multiply the sum of squares with the number of clusters stored. And so what it means is that you can do that plot, and then, for instance, for this case of 11 patterns, suppose you don't know that these are 11, right? You can try this scaling until it falls on that line, and then this gives you an estimate for the number of patterns stored. Shall we pay? I made a picture here so you can see that maybe more clearly. You see, this is exactly what I said. So really, you know that we have 22 patterns stored, and we do our analysis, assuming that the number of stored patterns was 22, larger 30, or smaller 12. And then the curves you get are the green one for more patterns, the blue one for less. And you see that this allows you to estimate the number of patterns which really are there. You want your curve to fit on that line, and that needs the KT to be 22. Okay, so we are almost at the end. So this is this is now the second method, to say something about the number of patterns stored in this network. And this is now using correlation matrices. So it's the same idea, right? You start with a lot of initial states, do this recovery process, and at the end you want to see how different are these vectors you get. And if there are patterns stored in this network, then you expect that the vectors are somehow similar. And of course, that means that you have correlations in your correlation matrix. Okay, so this is what I said. And now to try if this really true, we generate in that way many correlation matrices, 100 for each of those cases. So for the case where you have 50% filling, 100% filling, and 150% filling. For 40 neurons, it would mean 3 patterns in this case, 6 patterns in the 100% filling case, and 9 patterns in the 150% filling case. For 400 neurons, it would be 30, 60, and 90. Okay, and then, so overall, we have 300 correlation matrices, okay, 100 for each filling case, and we apply the k-means algorithm to all of them. And then, okay, here we choose k equals 4. And this, okay, this is for a reason I don't want to explain today. Anyway, there are no matrices in this column, so we can say let's choose 3 k equals 3, and then we would expect that the correlation matrices, which correspond to half filling, they would all fall into one cluster. The correlation matrices with 100% filling in another cluster, and with 150% filling in still another cluster. Right, and at least for a small number of neurons, this is in fact what you can observe. For a larger number of neurons, it seems that it does not work. And so it seems that if you increase the number of patterns too much, then simply the correlation matrices become indistinguishable. Right? So that would mean that you can distinguish the amount of patterns as long as you are below the capacity of the network. In this plot, we tried two different things. On this side, we use the eigenvalues for the clustering. So for each correlation matrix, we calculate the eigenvalues and look whether they are different or similar. And in this side, we really compare the matrices as such. But the results are practically the same. Okay, so these are the conclusions. But we reviewed first how does this Hopfield network work and how you can estimate its capacity. The problem with this network is that without prior knowledge, you cannot really retrieve the patterns which are stored there. And the solution, I mean, it's only a partial solution, at least to know whether there are patterns or not stored, would be, say, this clustering algorithm like to either the output vectors directly or to the correlation matrices between the output vectors. And as an outlook, we can try to get more precise estimates about the number of stored patterns and the amount of retrievable information. So I told you that the vectors you end up with in this retrieval process, they have something to do with the pattern stored, but one could try to quantify really how much information do they contain about the patterns originally stored. And of course, associative networks, they are usually used in context of non-random patterns, like photos, pictures from cats and dogs, for instance, right? And that's a very different issue then, right? Because from non-random patterns, it might be, or it probably is, much easier to retrieve them, right? Because you have redundant information in your picture. And okay, that's another question we eventually could look at. So that's all. Thank you very much. Questions?
I don't know. So how do you, could you please go back 3 slides? Next slide. So here you read the eigenvalues and matrices with k-means.
Yes.
So for the eigenvalues, you took the vector with the eigenvalues and use the k-means. And give you the same result.
Yes. In fact, I mean, that is something that one has to pay attention to for the matrices, right? Because the vectors are random and also the initial vectors are all random, so there is no particular order. So you cannot directly compare the matrices, you won't see anything. Because there is no way, your basis, there's no way to order it. Right? So what we did is we ordered no, let me try to get it right. Yeah, so we have 100 vectors, right? Each one comes from one recovery process, and then we order them according to the energy in this age of Y. And that then allows you to get well, to get some information about similarity. Otherwise, you
And usually in K-means, if you do the K-means with matrices and its eigenvalues, they give you the same results. In general, right?
no, it depends. So you see that if I would do that ordering, or if I couldn't, I mean, if there would be a process where this ordering cannot be done, the eigenvalues will give you something, but the vectors, the matrices, more questions? Let's call it a day.